When a system encounters more incoming demand than its internal pathways can process, it reaches a physical bottleneck. To manage this overload, we rely on a specific optimization strategy, job sequencing with deadlines. This logic is applied in CPU process management, cloud infrastructure, and airline logistics, environments where multiple high-value tasks compete for the same limited window of time. Because operational bandwidth is finite, it is often impossible to execute every pending task before its window closes. Since we cannot complete everything, our objective shifts from total task completion to selecting the specific subset of jobs that yields the highest possible value. To build an algorithm that can make these selections, we first standardize the work. We define a job as any individual task that requires a system's attention. Every job is defined by two variables. First, a deadline, designated as D, representing its target date for completion. Second, a profit, designated as P, representing its specific value. We then map the system's available capacity onto a linear timeline, divided into discrete units of time. This creates a core optimization challenge, identifying the specific set and sequence of jobs that yields the highest return within the available slots. Solving this challenge requires profit maximization, a method that mathematically guarantees the highest total value from a limited time frame. Before we can optimize, we must establish the physical rules of this scheduling environment. The first constraint is uniformity. In this model, every job requires exact 1 unit of time to complete. The second constraint is exclusivity. The system can only process one job at a time. Parallel execution is not an option. If we attempt to force a second task into an occupied slot, the system must reject it. Because these time slots are exclusive, every decision to schedule a job is a simultaneous decision to exclude another. Maximizing profit is therefore a process of selecting only the most valuable tasks that fit within the grid. It is a common mistake to assume a deadline is when a job should start. In an algorithmic context, the deadline is the absolute latest finishing time for a task. If a job's execution finishes even 1 second past this mark, the profit value drops to 0 and the job is considered invalid. The system only secures the value if the job completes its single unit of work before that cutoff. A high-profit job is worthless if we cannot secure a slot for it before its finishing threshold. The primary directive of the algorithm is to protect these high-value jobs from crossing that threshold. With dozens of jobs offering different profits and deadlines, we need a starting point for selection. We use a greedy approach. This means we prioritize the most valuable choice available to us right now. The first step is to sort the entire pool of jobs based purely on profit, from the highest value down to the lowest. Sorting tells us which jobs are the most valuable, but we still have to determine when to execute them to avoid wasting space on the timeline. To do that, we need a placement rule that prevents high-value jobs from blocking one another. Imagine we have a high-profit job with a deadline of 3. Slots 1, 2, and 3 are currently empty. The intuitive choice might be to execute this job immediately in slot 1. However, the optimal rule is to place the job in the latest possible available slot before its deadline, in this case, slot 3. By deferring flexible jobs to the end of their window, we preserve the earlier slots for jobs with tighter, more immediate deadlines. If we had used slot 1 for a job that could have waited until slot 3, we would have unnecessarily blocked a job that only could have fit in that first slot. This deferral maximizes the available surface area of our timeline, allowing us to fit more high-value work into the schedule. By repeating this process, sorting by profit, and then allocating the latest possible slot, we generate a schedule. A schedule is a validated arrangement where every chosen task is completed before its finishing threshold. This specific configuration provides the mathematical certainty that we have achieved the highest possible total profit from our data. The resulting sequence ensures that no deadlines are violated, and the total profit is as high as the initial dataset allows. For exam preparation, remember this logical flow: jobs, deadlines, Profit, schedule, profit maximization. A job is the task, the deadline is its finish time, and scheduling is the precise arrangement of those tasks within our constraints. Understanding the logic of the placement is the first step. The next is translating these rules into a functional algorithm. In Part 13, we will implement this logic, moving from theory into pseudocode, time complexity analysis, and a full numerical dry run. Mastering the conceptual model provides the foundation for the technical implementation to follow.